Good morning. I am Kiran, student of BSc Chemistry Honours final year. Today, I will teach you the lesson of hard and soft acid and bases. The term acid and base is routinely used in our daily life. Chemist has classified substance as the acid and bases since long time. Laboratory noted that the common element in all the acid was oxygen. The word oxygen in Greek means acid former. However, the Humphrey Davy shows that the acid contained hydrogen. It was 1884 Arrhenius developed a theory of acid and the bases. According to Arrhenius, the acid is a substance which gives hydrogen in aqueous solution, and the base is a substance which gives hydrogen ion in aqueous solution. The the strength of acid and base depend upon the capacity to provide H positive or OH negative respectively. The process of neutralization of acid and base can be represented by the reaction H positive OH negative gives rise to H2O. In 1923, J. Bronsted and the T. M. Lowry independent properties new acid and base theory. According to their theory, acid is a proton donor where the base is a proton acceptor. Acid-base reaction is neutralized is regarded as the electron transfer reaction. In 1923, G. N. Lewis gave another general definition of acid-base behavior in terms of the electron donation and acceptance. However, their theory got recognition only in 1930. According to Lewis, an acid is a substance which can accept a pair of the electron, while base is a substance which can donate a pair of the electron. The earlier definition of acid and base were based upon the observation properties such as the taste, ability to dissolve substance insoluble in water, and their effect on vegetable dyes. The term acid was applied to the substance that have a sharp or sour taste, turn blue litmus to that react with certain metal to liberate hydrogen gas, and have ability to dissolve substance insoluble in water. On the other hand, the testing and the filling chemical are dangerous methods of determining whether a substance is acid or base. You should never ever test of touch solution of chemical in laboratory. There are however other method of acid and the bases. For example, acid and the bases change the color of the certain dyes. Thus, any substance which has unshared pair of the electron can act as a Lewis base, whereas the substance which have empty orbital to accommodate a pair of the electron act as a Lewis base. In other words, substances capable of donating a pair of the electron are regarded as the Lewis acid, and the substance capable of accepting a pair of the electron are regarded as a Lewis acid. Lewis base or neutralization reaction may thus be regarded as the donor reaction or coordinate covalent bond formation reaction. The classical example of Lewis acid base reaction is that of between boron trifluoride and the ammonia. Using electron diagram, we can see that the boron trifluoride is the Levic acid and the ammonia is Lewis base. NH3 plus BF3 gives rise to NH3 with coordination bond with BF3. Lewis concept of acid and bases is very commonly used because of its simplicity and the ease with which the formation of coordination compound can be explained. In brief, all the usual legend can be regarded as the Lewis base, whereas the all metal ion can be regarded as the Lewis acid. The degree of affinity of the metal ion for the legend can be termed as the Lewis acidity, and the tendency of the legend to combine with the metal ion can be regarded as the Lewis basicity. Hard and soft acid and bases. An acid-base reaction, according to Lewis concept, involves the reaction between a donor and a acceptor is given below. A give reaction A and B is the reactant give rise to A and B. The formation of stable complex between the donor and acceptor depend upon the nature of the species A and B involved. It has been known since long that the certain legend form more stable complex with the metal ion such as Ag positive, Ag2 positive, Pd2 positive, platinum 2 positive. On the other hand, certain legend form stable complex with metal ions such as the Al3 positive, CO3 positive, Pt4 positive. Based upon the professional bonding, the acid and the base have classified into two groups, class A and class B, according to their preference. Class A metal ion includes alkali metal, alkaline earth metal, lighter and more highly charged ion, hydrogen ion. Class B metal include heavier transition metal of second and third transition series. Heavier transition metal in lower oxidation state. Low covalent metal ions such as the zero valent metal ion in the carbonyl compound. Depending upon the type of metal ion, legend can also classify as the metal class A and class B depending upon their preference. Class A legend include molecules of the ion with donor atom nitrogen, oxygen, fluorine, chlorine, etc. It is important to note that class legend prefer to form strong complex with class A metal. Class B legend includes molecules and ion with the donor atom phosphorus, arsenic, sulfur, selenium, iodine. Class B legend prefer to form complex with Class B metal ion. It was 1963 PSN coined the term hard and soft acid and bases for Class A and the Class B metal ion, the legend respectively. Accordingly, Class A metal ion are referenced to hard acid, while the Class B metal ion are called soft acid. Similarly, Class A legend are named as the hard bases, where the Class B legend are termed as soft bases. In summary, according to Bhasin, Class A acid are hard acid, Class B acid are soft acid, Class A base are hard bases, and Class B bases are soft bases. Bhasin observed that it is possible to correlate acid-base interaction on the basis of hard and soft. These called these acid and the bases as the hard. On the other hand, the type B metal ion and the legend they prefer appear to be larger in the size and more polarizable. He described these acid and bases are the soft. Pearson generalized the acid-base relationship and expressed that the hard acid preferred hard base and the soft acid preferred soft bases. Classification of the acid: a general classification of some common hard and soft acid along with the some broader line cases is given in the table. Hard acid are the hard acid are cation or smaller size. Hard acid are cation of higher oxidation state. Hard acid are the molecule or cation with lesser number of valence electron. Hard acid hold the valence electron tightly and not easily polarizable. In summary, hard acid binds strongly to a proton. Hard acid are small size, compact, and are not easily polarizable. A close look at the table 4.1 also reveals that the soft acid possesses the following characteristics. Soft acid are the cation of large size of heavier ion. Soft acid are the molecular ion with larger number of valence electrons. Soft acid do not hold the valence electron tightly and easily polarizable. In the summary, it is important to note that there is no sharp division between hard and soft acid. There are a number of acids that are neither too hard nor soft acid. Such type of acid that are neither hard nor soft are borderline acid, which are shown in the extreme right table 4.1. Borderline acid have the property which intermediate between that of hard acid and hard base. In case of the borderline acid, the properties such size, oxidation state, and the polarization of the cation molecule are neither too low nor too high. On the other hand, the soft acid will show the opposite trend, and the following order of preference for binding the donor atom ion with a group is observed. Classification. Now, Pearson hard soft acid base principle. Pearson proposed a simple rule for predicting the stability of coordinate compound formed between acid and the base. It is important to note that the hardness of softness of the acid and bases they refer only the harder and the source of interaction. It is by no means related to the strength of acid and the bases. For example, both F negative and OH negative ion are hard bases, but the strength of OH negative is 10 power 13 times than the fluorine ion. Application of the hard soft acid and the bases. Stability of the complex. We have already noted that the hardness and the softness of the acid and bases are related only to hard and the source of interaction. Hardness and the softness of the acid and the bases has nothing to do with the inherent acidic and basic strength of the acid and the bases. Both the OH negative and the fluorine ion are the hard bases. All the OH negative ion for the stronger A base than the fluorine ion. In fact, OH negative ion is 10 power 13 times more stronger than the fluorine ion. PS in 1963 explained the relative stability of the coordination compound on the basis of hard soft acid and the base principle. Let us consider a general reaction between the acid Lewis acid and the Lewis base. The complex AB will be more stable if the AB are either both hard and the soft. The complex AB will be least stable if the A hard and the B is soft. A is soft and B is hard. For example, complex between a soft acid AZ positive and the soft ion negative ion are quite stable. In contrast to one between the soft acid Ag positive and the hard base F negative. Ag positive plus 2I negative gives rise to AgI2 negative. The rate of the thumb is determined the stability of the complex is preferentially formation of hard and soft interaction. Why COF63 negative complex is more stable than the COI63 negative. In both the complexes, the oxidation state of cobalt is +3. Cobalt +3 is the hard acid. Therefore, combination of hard base fluorine ion will lead to COF63 negative, which is hard interaction. On the other hand, combination of CO3 positive with soft base I negative will lead to COI63 negative, which is a hard soft interaction. COF3 is more stable than the COI63 negative. It has also been noted that the combination of hard or soft reagent with a metal ion is always preferred over a combination of a mixture of hard and the soft reagent with a metal ion. For example, the complex are far more stable than the complex these. This is because the CN negative and the I negative, both soft base and NH3I negative, are both hard bases. Classification of acid and the bases. The acid and the bases can classify as the hard and the soft depending upon their preference to hard and the soft reactant. BH positive plus CH3H positive gives rise to CH3HGB positive plus H positive. The definition of hardness primarily uses the idea of the polarity, which states that the less polarized species is hard and the most easily polarizable is soft. For an ion of the similar charge, the ratio of charge to radius should be used to assess the relative polarizability, relative hardness of the substance. However, the hard, soft, acid and base principle does not take into consideration the quantitative idea of the relative hardness and the softness of the species. In summary, the major limitation of hard, soft, acid and base principle are hard, soft, acid, base principle is too general and without any quantitative scale of the measurement. Hard, soft, acid and base principle does not take into the consideration the acid or basic character of the compound. It failed to explain the feasibility of the reaction. CH3 positive plus H2 gives rise to CH4 plus H positive. It is a probability of greater acidity of proton H positive related to CH3 positive cation is responsible for the unfavorable reaction. Limitation of the hard soft acid base principle. The hardness and softness of acid or base is primarily related to stability of hard and the soft interaction. It has no concern with the acidity or basicity of the acid or base. For example, OH negative and fluorine are well known hard bases. Therefore, basicity of the hydroxide ion OH negative is very large as compared to fluoride ion. In fact, the basicity of hydroxide is 10 power 13 times than the fluoride ion. A strong acid is well known to display a weak acid. For example, the reaction between a sulfide ion and the hydrogen sulfide proceed in the forward direction. It means that the stronger base SO3 to negative 10 easily displace the weaker base F negative ion. Acid is well known to display a weak acid. For example, the reaction between a sulfide ion and the hydrogen fluoride proceed in the forward direction. It means that the stronger base SO3 to negative can easily displace the weaker base F negative ion. From the acid hydrogen fluoride, SO3 to negative plus HF gives rise to HSO3 negative plus F negative. However, the above reaction is favored according to the hard soft acid and base principle is detailed below. SO3 to negative plus HF gives rise to HSO3 negative plus F negative. which only favor hard and the soft interaction. Similarly, a very strong base can displace a weak base from a soft acid. Methyl mercury OH negative plus CH3HgSO3 negative gives rise to CH3HgOH plus SO32 negative. However, the above reaction is also not favored according to hard soft acid base principle, which only favor hard and the soft interaction. In the both of the above cases, it is inherent strength of the bases SO32 negative is greater than fluorine ion than hydroxide in the sulfide. That forces the reaction in the forward direction in spite of the less preference formation of hard software in the product. This is true in case especially when the inherent strength of the base being compared as the significance different. The order of basic strength being OH negative, then SO32 negative, then fluoride. In other words, significant difference between strength force of the reaction against the basis of hard soft interaction. However, when both the strength of acid and base and the hardness softness are not significantly different, then the acid base principle work well, resulting in the product having hard and the soft combination. For example, CH3HgF plus HSO3 negative gives rise to CH3HgSO3 negative plus HF. CH3HgOH plus SSO3 negative gives rise to CH3HgSO3 plus HOH. It is important to mention that the inherent strength of acid and bases should not be ignored while the applying hard soft acid base principle. Symbiosis. The hardness and softness of acid or base entry is not an inherent property but depend upon the substituents. The ammonia is a hard base while the pyridine is a borderline base. The acidic B3 positive ion is borderline between the hard and soft acid. Addition of the three small size non-polarable substituents like fluoride make a hard Lewis acid, whereas the addition of electron donor acid base group like the hydride ion make it a stronger Lewis acid. The difference in the hardness and softness of BH3 BF3 can be the difference in the hardness and softness BF3 and BH3 can be illustrated nicely in the following example. R2S BF3 plus R2O gives rise to R2O BF3 plus R2S. R2O BH3 plus R2S gives rise to R2S BH3 R2O. Johnson observed that the hard ligand have a tendency to combine with a metal ion having hard ligand, and the soft ligand have a tendency to combine with a metal ion already have soft ligand. He coined the term symbiosis for the such interaction. The hard BH3 molecule prefer to combine with hard base F negative and the tetrafluorobutane BF4 negative, as the soft acid BH3 prefer to combine with a soft base H negative and to give a tetrahydrobutane BH4 negative. BF3 plus F negative is equal to BF4 negative. BH3 plus H negative gives rise to BH4 negative. B2H6 plus 2H negative gives rise to BH4 negative. An important outcome of symbiosis is that the symmetrical substitution group are formed in preference to the unsymmetrical substituent group compound. For example, compound containing mixed substituent interact strongly to the real symmetrical compound with the same substituent as given below. BH3F negative plus BF3H negative is rise to BF4 negative plus BF4 negative. Similarly, as the fluorination methane react with give symmetrical methanes, CH3F plus CH3H gives rise to CH4 plus CF4. In brief, symbiosis may be defined as the tendency of the soft ligand to combine with a metal ion already having soft ligand, and the tendency of a hard ligand to combine with a metal ion already having hard ligand. Theoretically, basis hardness and softness as hard HSAB principle. Electrostatic interaction theory. According to this theory, hard acid and hard base are from purely ionic compound. Therefore, the hard interaction are purely ionic or electrostatic. Most of the hard acids such as Li positive, K positive, and the hard base is O negative O2 negative fluoride and hydroxide ion, well known to form ionic compound. We know that the electrostatic energy of the ion pair is inversely proportional to the interatomic distance. It means the smaller the ion, smaller will be the internuclear distance, and greater will be the electrostatic energy between the ions. As a result, the final compound formed by the hard acid and the hard base will be highly stable. Polarizing power and the polarizability. Electrostatic interaction can't explain the source of interaction because of the bigger size of the source. Therefore, the interaction between the large size acid and the base must involve covalent character. Almost all the acid have 6 or more d orbitals. Soft acid with T10 configuration are excellent soft acid. The bonding between soft acid and soft base is largely covalent. Nature occurrence of the ore and the mineral. Nature occurrence of ore of the certain metal can be easily explained on the basis of the HSAB principle. Hard acid metal ions such as Mg positive, aluminium, chromium, the frequently occur at their oxide, fluoride, chloride, and carbonate. This is primarily due to their preferred hard acid hard base interaction. We know that the oxide and the halide and the carbonate are all hard bases. These hard acid metal ion can't occur as the sulfide because S2 negative is a soft base, and on the other hand, the soft metal ions such as the Cu positive, Ag positive, Cd2 positive occur invariably in the ore as the sulfide due to the soft acid soft base interaction that result in the formation of the stable complex. Interestingly, the borderline acid like the CO2 positive, Ni2 positive, Zinc2 positive can occur both as the sulfide as well as their oxide and the carbonate as a result of their intermediate character. Catalytic poisoning. All metal atoms are soft acid. Some of the metal, namely chromium, nickel, platinum, palladium, well-known catalysts. These metal catalysts have been found to be easily poisoned of the soft. In fact, the strong reagent are absorbed strongly on the surface of metal and block the reactive sites by forming metal complex. In other words, the metal atoms lose their activity and are said to be poisoned. Thus, the soft basis complex with the metal in atomic state will act as a poison toward the metal catalyst. Electronegativity and the hardness and the softness are related to electronegativity. Species with higher electronegativity value are assigned greater hardness, and those with lower electronegativity value are assigned greater softness. Electronegativity constantly means the power of an atom in a molecule to attract electron toward itself. However, in such case, it refers to power of an individual ion participating in the reaction. For example, lithium atom is known highly electropositive metal, but the cationic species Li positive has greater tendency to attract the electron toward itself. As a result, Li positive is considered to be more electronegative, hence is a hard acid. On the other hand, the heavier transition metal ion oxidation state have relatively low second ionization potential. Using the some concept of electronegativity, we can define hard and soft bases. Mulliken Jaffe defined electronegativity as a linear function of partial charge developed on atom according to Hi equal to A plus B delta. Here A is the electronegativity of an atom, B is the rate of change of electronegativity with the charge. The electronegative value of A atom is similar to the Pauling and the Rockow parameter. B is called charge coefficient. Small, hard, and non-polarizable atoms have higher value of B, whereas the large and soft and polarizable atoms have smaller value of B. Parr and the Pearson introduced a new term as the absolute hardness for the neutral as well as the charged species and correlated it with the absolute electronegativity. The absolute hardness is defined as one half of the distance between ionization energy and the electron affinity. Here neta equal to I minus A upon 2. I is ionization energy, A is electron affinity of the species in question. Here the Mulliken defines the electronegativity is psi equal to I plus A upon 2. The hardness of base B and the acid may be given as the neta B equal to 1 half IB positive minus AB positive. For species A, half equal to I A minus AA. In order to understand as to why in the equation 4.6 the base B is represented as B positive, whereas equation 4.7 acid A is represented as the A. Let us consider the interaction of acid A and base B to form the compound AB. Here A plus B gives rise to compound AB. In the formation of the compound AB, electron will move from B to A, which is indicated by the partial positive and negative charge. Hardness of the B refers to a species going from del positive to a charge 1 plus del positive, while hardness of A refers to a species on ionization from del negative to a charge 1 plus del negative. If the shift of the charge del is taken as equal to 0.5, then the charge on the B becomes 1 plus 0.5 gives rise to 1 plus 1.5, and on A become 1 plus minus 0.5 gives rise to 0.5. Thus the charge on the B changes from 0.5 to 1.5 with the average 1 upon 2 into 0.5 plus 1.5 gives rise to 1, and that of A change from minus 0.5 to 0.5 with average 1 half 0.5 minus 0.5 that is equal to 0. Thus that justifies the reason why species B is shown as B positive and A is shown as neutral in the equation 4.6 and 4.7. However, there are certain example is any value of Ti3 positive is to be harder acid, whereas the Tl3 positive is well known to chemically softness. However, a comparison of Tl3 positive with other trivalent ions show the accepted soft character. Soft acids are generally transition metal in low oxidation state containing loosely held d electron. These electrons can be easily donated to the ligand. On the other hand, soft bases are pi bond acceptors such as the CO R3P alkene alkyne. In the soft acid base interaction, pi bonding is very important. Sigma bond formation due to the donation of the electron from the base to the metal is reinforced by the pi bond donation for the metal to the base. Relation to molecular orbital theory. Molecular orbital theory is a powerful tool for explaining structure and bonding visual UV spectra and the detailed mechanism of the chemical reaction. The concept of absolute electronegativity and the hardness can also be explained using molecular orbital theory MOT. The ionization energy is measure of the energy of highest occupied molecular orbital HOMO, whereas the electron affinity is measure of energy of lowest unoccupied molecular orbital LUMO with the charge in sign for a given molecule. According to Koopman theory, IHOMO gives rise to minus ionization energy E, and E equal to LUM gives rise to minus electron affinity. The hardness and the softness depend upon the average gap between HOMO and the LUMO. The combination of soft acid with the soft base is analogous to the situation in which the lowest unoccupied molecular orbital of the Lewis acid has about the same energy as the highest occupied molecular orbital HOMO of the Lewis base. The combination of the orbital result in greatly reduced energy for the electron pair coming from the base as shown in the figure 4.2, thus giving a strong covalent bond. In the figure, we can see that the representation of the comparative orbital energy for A is the soft acid and the soft base combination, and second one is the hard acid, the hard base combination. That is all about the hard and soft acid and bases. Thank you.